Hello, hello, hello. This is Nicholas with Calculus Trent Style number 2. And have you heard about the prisoner's favorite punctuation mark? Well, it's the period, of course, because it marks the end of his sentence. Anyways, in the last video, I did a lot about limit theory and what limits are about, but I didn't really go through very many problems of actually working out limits. So that's what I'm going to do in this video. So I guess I'll call it algebra with limits. And so what I'm going to start with is the following limit. It'll be the limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x. So the first tactic you might try is directly substituting into the limit, right? If the function is continuous at the point that we're approaching at, in other words 2, then you can just directly substitute and get the answer. So if we do that, though, we get 2 squared, which is 4, plus 2 times 4, which is 8, minus a 12, over 4 minus a 4. In other words, we get 0 over 0. Dun, dun, dun. This is what's known as an indeterminate form. Why is it indeterminate? Because the answer cannot be determined. There's infinitely many answers to this expression. Why? Because let's say 0 over 0 is equal to some number x. Then that means that 0 is equal to 0x, just multiplying by a 0 here. And this here is true for every value of x, even in the complex numbers or even in the four-dimensional quaternions. All right, it's true for everything. So their answer to this could be whatever you want it to be. So since it cannot be determined, we call it an indeterminate form. Some other indeterminate forms that you just need to know are, this one shows up a lot. If we have infinity over infinity, that's indeterminate. I'll elaborate on why that is. Infinity minus infinity, it's not equal to 0, not 0. Despite what you might hear, it's not 0. 0 to the 0, or 0 to the 0th power. So anything raised to the 0th power is 0, except for 0. And 1 to the infinity. Am I forgetting any other ones? Those are the main ones that pop up, really. Yeah, I'll leave it at that. You don't see too many other types. So let me give you an example. So let me first start out with infinity minus infinity. And this is poor notation because infinity is, well, infinity is complicated because infinity is not a number, but it's not a number. See, sometimes you can treat it as a number, and sometimes you can't. It's really what it comes down to. Let's say, though, that you thought infinity minus infinity is equal to 0, okay? Then what I could do, since this equation is true by equality, I can add 1 to both sides. And I can put parentheses here. And since this is really a negative 1 because of that negative sign there, I actually just subtracted a 1. So this should be a negative 1 here. Now, so I really subtracted 1 from both sides. So now, what's inside the parentheses is, if you add 1 plus infinity, what do you get? You still get infinity, right? You take, maybe it might be interesting to, if you take a look at Hilbert's paradox of the Grand Hotel. If you're familiar with that, then the idea is, well, take infinitely many guests in accountably infinite many hotels, and you can take the guests in room 1 and move them to room 2. You can take the guests in room 2 and move them to room 3, the guests in room 3 and move them to room 4, and so on. And since there's infinitely many rooms, you will have now created a new spot in the very first room, so now you can put the new guest in to that room. So that's just kind of an analogy, I guess, to support my claim that infinity plus 1 is still infinity. Or infinity plus any constant is still infinity. Or infinity times any constant is still infinity. So then what I can do is I can just write this as infinity minus infinity, since this part here is just infinity, and that's equal to negative 1. But wait, we just said it was 0. That would mean that 0 is equal to negative 1. No, that's not true. So infinity minus infinity is an indeterminate form. Okay, infinity over infinity. This is really saying, well, let's say you think it's 1, right? That would be the, I guess, your first instinct, right? Because anything over itself, at least in the real numbers, except for 0 over 0, is just 1, right? 2 over 2 is 1, 3 over 3 is 1, so on. If you said that this were 1, then that would mean that if you just by the definition of division, that would mean that infinity minus, if you were to subtract infinity an infinite amount of times, you would get 1. That doesn't even make sense, first of all, but you would have infinity minus infinity minus infinity dot 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 minus infinity, and you would have this infinity times for whatever that means, and you would say that's equal to 1. Well, you could group these, and each one of those groupings is indeterminate because you'd have infinity minus infinity. Long story short, infinity over infinity is also indeterminate. Okay, let's take 0 to the 0. Well, 0 to the 0 is really, 0 to the 0 is really 0 to the 1 minus 1, right? Exponent properties, which is 0 to the 1 over 0 to the 1, also exponent properties, which is 0 over 0. And that is an indeterminate form, like I said up here. So 0 to the 0 and 0 over 0 are really the exact same thing. They're just both indeterminate. And now 1 to the infinity, it's a little more uncommon of an indeterminate form. For example, let's take the limit as n approaches infinity of 1 plus 1 over n to the n. So as n gets bigger and bigger and bigger and bigger, what does this limit approach? Well, this limit is actually the limit definition of E, Euler's number, which is approximately 2.71828, and don't think it repeats, it's 2.718281828.459, so it doesn't repeat with just the 1828s. But in other words, 1 to the infinity is not necessarily 1. It can go to 0, it can go to 1, or it can go to E. So why did I elaborate on all that here? Just so that you recognize that when you see these forms here that I'm writing down right now, when you see these forms, you need to do more work with the limit to get it out of an indeterminate form. And these, truthfully, will become very common throughout calculus, but and you'll probably just naturally memorize them, but they do need to be recognized very quickly. So, with all that out of the way, we can now do the actual limit. So, we need to get rid of this 0 over 0. How can we do it? Well, the common idea is to write it as, still the limit. We can factor the numerator as x plus 6 times x minus 2 over x times x minus 2. And now you'll notice these factors go away. We can cancel them out. And we can cancel them out because they're 1. Anything over itself is 1. Although this limit is approaching 2, we don't actually plug in 2 for x. If we did actually plug in 2 for x, then what we would cancel out would be 0 over a 0. But we don't care about actually what's happening at 2. We care about what's happening as we approach 2. So we can indeed cancel out these factors of x minus 2. And this is what's making the limit 0 over 0, because notice, if we were to plug in 2 directly like how we did up here, we get 0 for this factor times Schmozkin, whatever that is, over 0 times a Schmozkin. So we're going to have a 0 over a 0 here. And so that tells us that that is what's making this limit indeterminate. Oopsies. If we get rid of that factor of 0, then we then just get, oh, my pen is thicker now. The limit as x approaches 2 of x plus 6 over x. Oh, I wrote a 6 over x. And that is easily done. You can just substitute in 2. So we get 2 plus 6, or 8, over 2, or 4. And that's the answer to that limit, is 4. Now, truthfully, this would be a very simple problem. I just went through and explained all the indeterminate form stuff as kind of a necessary background information to have. As another one, let's do an example. The limit as h approaches 0 of 2 times negative 3 plus h squared minus 18 over h. One thing I would just like to note is that we can actually factor a 2 from the numerator, and we can get the limit as h approaches 0 of 2 times negative 3 plus h squared minus 9 all over h. And hopefully this should make sense. We can actually put, if we're multiplying by a constant within the limit, we can just put that up front and make it 2 times the limit as h approaches 0 of negative 3 plus h squared minus 9 over h. And why can I pull out this constant? I can pull it outside because imagine this. Imagine I have a function, any generic function, say x squared, and let's say I'm considering the limit at 1. So let's say this point's 1. If I multiply it by 2 and I get 2x squared, all that's going to do is just make it grow up quicker, right? So instead of having a value of 1, it'll have a value of 2 here. And so you can see that when we take this limit at 1, it's just 2 times the limit of this original function where we didn't multiply by that extra factor of 2. So in general, when you have a constant out that you can factor out, you can pull it out front of the limit. Okay, now this is 2 times the limit as h approaches 0 of, now we square the first one, we get 9 minus 6h plus h squared minus a 9 over h, which is 2 times the limit as h goes to 0 of, now the 9 and the 9, they go away, and I can make it h times, that looks like a 6. It can be h times h minus 6. See this, h squared minus the 6h. I pulled a factor of h out. And now we are dividing by h. And so now notice that if we were to plug in 0 originally into the original limit, and you were to try it by direct substitution, then you would notice that you would get 0 over 0. How do I know I would get 0 over 0 without even plugging it in? Well, I notice because I have this h over h here. And so when I plug in h for 0, I get 0, and likewise on the denominator. So you would get a 0 over 0. So we can cancel these out, and we can just get 2 times the limit as h approaches 0 of h minus 6, which now we can easily just substitute in, right? We get 2 times negative 6, or just negative 12. And that's the answer to that limit. Okay. One more common type of limit. Factorizing is really helpful, right? Maybe as an example, let's say we have the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, I just pulled this out of thin air, but how did I pull that out of thin air? Well, because I know that x squared minus 4 factors into x plus 2 times x minus 2 over x minus 2. And then I could cancel out the factors and then get my answer of 4. So a lot of times that's what they'll do in these problems is they'll, if you are, upon factorizing, you'll get one factor over another over that same factor, which will cause you to get an indeterminate form when you originally substitute directly. And that's what they'll kind of do in their heads. Also, the sum and difference of cubes is also very helpful if I have the limit as x approaches 2, let's say x cubed minus 8 over x minus 2, then I could make, don't forget the limit. We're still taking the limit as x goes to 2 of x minus 2 times x squared plus 2x plus 4. This is the difference of cubes. If you don't remember that, it's a cubed, and you need to remember it, it's a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So, and we're dividing by an x minus 2. Wow, x minus 2. And then we could then cancel out those factors of x minus 2 and then just plug in 2. So we get 2 squared, which is 4, plus another 4, plus another 4, for an answer of 12. One more common type of limit is the following. Let's say we have the limit as t approaches 4 of t minus the square root of 3t plus 4 over 4 minus t. In general, when you see this type of limit with the square root, almost always, in fact, I honestly can't think of a counterexample to the claim I'm about to make. Just multiply by the conjugate of the numerator and the denominator to get rid of the square root. In other words, multiply by t plus square root of 3t plus 4. And you have to do the same on the denominator because you're really multiplying by 1, which is always allowed. So I multiplied by the conjugate of the numerator, and so now I know that this and this are the difference of squares. So I don't have to go through all the foiling. I can just square the first term, t squared, put a subtraction sign, and then square the second term. So that's 3t plus 4, because the square of the square root of 3t plus 4 is 3t plus 4. And on the bottom, now I have to do some work. So 4 minus t times t plus square root 3t plus 4. Oh my goodness, I forgot the limit. We're still taking the limit. Don't forget the limit. The limit as t approaches 4 of all that schmozkin. So we get the limit as t approaches 4 of t squared minus 3t minus 4. Or in other words, I'll write it as instead, it factors, right? If I write it t squared minus 3t minus 4, that factors into t minus 4 times t plus 1. So we have t minus 4 times t plus 1 over 4 minus t times t plus square root 3t plus 4. Now you're saying to yourself, well, what? I don't see any of the same factors, but this t minus 4 and this 4 minus t look awfully similar. Well, actually, they are almost the same except for a negative sign. In fact, you can just cancel these out and instead just put a negative sign. Why? Because if I have t minus 4, wow, it looks like I'm writing in hieroglyphics or something. T minus 4 over 4 minus t, well, I could make the t minus 4, I could make the 4 minus t on the denominator the negative of t minus 4. And now you see that I can cancel out these factors of t minus 4, and I'm just left with a negative sign. So in general, if the terms are flip-flopped like how they are now, you can just cancel them out and put a negative sign. And I can also put that negative sign out front, so I can get the negative of the limit as t approaches 4 of t plus 1 over t plus square root of 3t plus 4. And now I should be able to directly substitute. So if I plug in 4, I get 5 over 4 plus the square root of 3 times 4 is 12 plus another 4, that's 16. Take the square root, you get a 4. So 5/8 is the answer to that limit. So some general properties I just want to list out plain for you is that if I have the limit as x approaches a of f of x, some function of it in terms of x, times some constant c, I can make that c times the limit as x approaches a of f of x. If I have the limit as x approaches a of f of x plus g of x, that's the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So you can separate the limits. This should make sense intuitively. And likewise, if this were minus, then this would be a minus here. I think in the next video, I will do some limits at infinity.